Hello everyone, thank you for attending my talk. My name is Mohannad Ismail, and today this is the presentation of our work titled Tightly Seal Your Sensitive Pointers with PACTight. This is joint work with Andrew Quach, Christopher Jelesnianski, Yeongjin, Jang, and Changwoo. So ARM processors have been increasing in popularity in recent years due to their entrance into the desktop and data center market. This expansion exposes ARM more than ever to security attacks, and thus it's becoming increasingly important to have effective and efficient defenses for ARM in these new environments. Many of these security attacks are due to memory corruption vulnerabilities. In a study done by Microsoft on its products, they reported that 70% of all security bugs found were due to memory safety issues, and 30% of bugs in Google's open source were memory safety bugs. So let's take a look at some background and related work, and I'll start with some attacks. Here I will introduce two attacks based on violating memory safety: control flow hijacking and use after free attacks. Control flow hijacking attacks aim to maliciously change the legitimate control flow of a program. And this can be done either by corrupting indirect calls or jumps, or corrupting return addresses. And this allows the adversary to execute an illegitimate control flow transfer that can reach, for example, a system call. Use after free attacks are temporal attacks aimed to exploit the incorrect use of dynamic memory. A pointer is allocated on the heap and can be used legitimately by the program. And when the memory is freed, the pointer becomes dangling and can be exploited by an attacker. To help combat abusing pointers, ARM released Pointer Authentication. Pointer Authentication relies on utilizing the unused bits of a 64-bit pointer to store a pointer authentication code, or a PAC, that is generated by a cryptographic hash function. The PAC cannot be calculated without a secret key, and this allows the pointer to be signed by this PAC. And thus, the PAC needs to be properly removed or authenticated before the pointer can be used. So how does this mechanism work? There are two main primitives. The first is the signing of the pointer. The cryptographic hash algorithm takes a secret key, the pointer, and the modifier, which is provided by the program. And the secret key is initialized by the kernel and stored in a register. The algorithm then computes the PAC and places it on top of the pointer. Then when a pointer needs to be authenticated, the algorithm takes the same exact inputs again and regenerates the PAC. If the PAC matches, then the PAC is removed from the pointer and the pointer can be used. However, if the authentication fails, the top two bits of the pointer are flipped, thus rendering the pointer to be unusable. Any change in any of the components passed to the cryptographic algorithm will result in a different PAC, and thus a failed authentication. There have been several defenses proposed very recently that utilize pointer authentication. I'll quickly go over their main points of interest, but this is pretty simplified, so please read the respective papers for the full technical details. The first one is part CFI, which offers forward and backward edge control flow protection. Its modifier is the stack pointer with a function ID for return addresses and a type ID for indirect code pointers. Next, we have PACStack, a defense mechanism that protects the backward edge. Its modifier is the previous chained return address on the stack. And last, we have PTAuth, which is a temporal defense mechanism for protecting against dynamic memory attacks. Its modifier is a generated object ID for each heap object allocated. And one quick observation in these defenses is that they put a lot of emphasis on the modifier, and thus this showcases its importance. There are limitations present in the current state of the art. One limitation is the reliance on a modifier that can be repeated. This means that attackers can reuse the PACs that are generated. Another limitation is needing a forward edge CFI technique to be present, so that the attacker cannot skip the instrumentation. And another limitation of some techniques is the reliance on a weaker threat model with only arbitrary read. So the attacker must not have the attacker must not have arbitrary reads for the defense to be viable. There are many limitations in the current state of the art with plenty of room for improvement. So now I'll introduce our solution, PACTight. So based on the limitations I mentioned, we identified 3 security properties in pointers that, if enforced, completely protect pointers from being abused. And they are unforgeability, in which a pointer must always point to its legitimate object; non-copyability, meaning a pointer can't be used at a location other than its legitimate one; And finally, non-dangling, meaning that a pointer cannot be used after its object has been freed. Enforcing these three properties tightly seals the pointers from illegal use. So let's take a closer look now at the three properties to better define them. Starting with forgeability, forgeability means that a pointer that points to a specific object becomes corrupted with a forged pointer that points to another object. And copyability means that a maliciously copied pointer can still be legitimately used to point to an object. And dangling means that the pointer of a freed or realloced object still points to that object and can be used by an attacker. Powerful memory corruption attacks are a direct implication of violating these three properties. And an attacker can generate packs with forgeability, they can reuse valid pointers with copyability, and they can reuse invalid pointers with dangling. The importance of these properties stems from the fact that in order to hijack control flow, at least one of these properties must be violated based on our analysis. And so PACTight seals pointers and guarantees that they cannot be misused. PACTight also overcomes the limitations of previous approaches. The non-copyability property prevents any pack reuse. PACTight protects all globals, stack, and heap variables. And PACTight assumes a strong threat model with arbitrary read-write capabilities. Next, let's take a closer look into the design. So how will PACTight enforce the three properties? PACTight relies on the Pointer Authentication modifier. And this modifier is used by the cryptographic hash algorithm to generate the pack, as I mentioned. And the reason we rely on it is that it's controlled and can be made complex enough to generate a unique pack. Any modification to it or the pointer would result in a violation. So PACTight blends the address of the pointer, %p, and a unique random tag generated by the PACTight compiler and associated with the memory object to enforce the three properties. So for signing, we incorporate these elements into the modifier. So the cryptographic algorithm modifier takes the location of the pointer and the random tag. And the same way for authentication, as can be seen, to regenerate the pack successfully. So now I'll explain how this choice of a modifier enforces the three properties. Starting with unforgeability, the pack mechanism on itself includes the pointer as one of the inputs to generate the pack. And thus, a forged pointer would trigger a fault on authentication due to the pointer having a different value from the one that was used for that pack. And then for non-copyability, the location of the pointer being included as part of the modifier means that any copied pointer will generate a different pack on authentication due to a different %p, thus resulting in a mismatch on authentication. This means that a pointer can only be used at its legitimate location, enforcing the second property. To enforce the non-dangling property, PACTight assigns a random tag to the pointer. This random tag is generated upon allocation and changes when an object is freed or reallocated, thus allowing the lifecycle of the object to be tracked. And a dangling pointer being used will not have a tag, and thus the pack generated on authentication will not match, resulting in a violation and thus preventing any misuse of dangling pointers. Taking a look at the structure and overall design, PACTight's security properties are used as a framework to instrument programs. And the instrumentation itself depends on how broadly the properties will be applied. And PACTight is composed of the PACTight LLVM pass that does static analysis on the LLVM IR and instruments the program with PACTight's functions. The result is an instrumented and a protected program. And this is a simplified example for the sake of the presentation, but we have more details in our paper. So next, I'll talk about PACTight's defense mechanisms. PACTight can easily be applied to protect a variety of pointer types. And the PACTight compiler automatically instruments all the globals, stack variables, and heap variables, as I said. So we chose to implement 4 PACTight defense mechanisms to demonstrate PACTight's versatility and coverage. I'll only be explaining PACTight code pointer integrity, or PACTight CPI, but PACTight is versatile and can also be applied to enforce control flow integrity, to protect C++ vtable pointers, and to enforce return address protection. More details on that are in the paper. So PACTight CPI guarantees the 3 properties for all sensitive pointers. And in this context, sensitive pointers are all code pointers and all data pointers that point to code pointers. And the sensitive pointers are authenticated only at legitimate sensitive sites. Otherwise, the pointer has a PAC on it and it cannot be used. PACTight CPI relies on LLVM static analysis for instrumentation, and it recursively looks inside all elements of a composite type to guarantee coverage. Next, we take a look at the evaluation of PACTight. We evaluate PACTight by answering the following questions. How effectively can PACTight prevent not only synthetic attacks, but also real-world attacks? And how much performance and memory overhead does PACTight impose? For the sake of time, I'll only go through the performance evaluation, but the full security evaluation is in the paper. We ran PACTight with 3 sets of benchmarks, the Spec CPU 2006, NBench, and CoreMark. We also ran one real-world application, NGINX, which is a web server. And the following graph shows our numbers for the different PACTight defense mechanisms, and as can be seen, PACTight has low average overhead across the board. We also evaluated memory overhead of PACTight CPI on the spec benchmarks and got a 19% memory overhead on average. And finally, I will conclude. I have introduced PACTight, which is an efficient and robust mechanism that utilizes ARM's pointer authentication primitives to guarantee pointer integrity. We identified 3 security properties that PACTight enforces. We showcased PACTight with 4 defense mechanisms that protect a wide variety of security-sensitive pointers. We also evaluated PACTight against real-world and synthesized attacks, and like I said, more details are in the paper on those. And we showcased its low overhead on a variety of benchmarks, and we used real PAC instructions. Also, I spent my PhD during COVID, and this is the first in-person conference that I attend. So please feel free to reach out to me and connect. I'd be more than happy to connect with all of you. And thank you very much for listening to my presentation, and I will gladly take any questions.